Okay, so the next thing we're going to be talking about are numerical methods for partial differential equations. But in order to do that, it's first useful to know something about how we go about classifying the types of partial differential equations, because that has an impact in terms of the type of methods we use for them. So I'm briefly going to talk about this idea of classification of partial differential equations, of linear partial differential equations. All right, so there are a number of canonical examples, it's like, of each of these classes, so I'll write them down. It's like, and then I'll explain something about their properties. So there's the wave equation. So it looks like UTT minus c squared uxx is equal to 0. So this is an example of what is called a hyperbolic partial differential equation. Then also there is the heat equation. Okay, so that looks like ut minus gamma uxx is equal to 0. So this is a parabolic equation. Then there's Laplace's equation. Which looks like uxx plus uyy is equal to 0. So I should mention that when I say UTT, I mean the second partial derivative of u respect to t. Uxx is the second partial derivative of u respect to x, and so on. And this is an elliptic equation. Okay. All right. So so let's say something about these things. So equations sort of governing things like vibrations. For example, the wave equation. Is typically hyperbolic. Okay. Equations modeling things like diffusion. Such as the heat equation. Is typically parabolic. So typically parabolic. Okay, and things which model things involving equilibria. Such as sort of the Laplace and Poisson equations. Are typically elliptic. Okay. All right. So so again, it's like things which are typically hyperbolic involve things which involve things like vibrations. things which involve sort of diffusion tend to be parabolic, like the heat equation, and things which describe some sort of equilibrium solution, such as Laplace's equation, are typically elliptic. Okay. All right. So so let's now see how where these classifications come from. All right. Okay. So let's consider a look at real linear second order partial differential equations for a scalar function in two variables. Let's call that u tx. Okay, then sort of the most general form is as follows. Okay, so you have L acting on U, so linear operator acting on U is AUTT plus BUTX plus CUXX plus DUT plus EUX plus FU is equal to 0. Oh, it's actually equal to G. Okay. All right. So the coefficients A, B, C, D, E, and F are allowed to be functions of T and X, as is the inhomogeneous term which is G, again, T of X in general. Okay, so the equation is homogeneous. If G is identically 0, right? And then we have to assume that at least one of A, B, and C is not identically 0. So assume that at least one of A, B, or C is not identically 0. So that it actually is an honest to goodness second order partial differential equation instead of something which degenerates to a first order partial differential equation. All right, so anyway, so the basic idea then is that you can look at a sort of a discriminant. So you consider the discriminant delta is equal to b squared minus 4ac. All right. And so depending on the value of this, it's like that leads to the different types of partial differential equations. Okay, so all right, so let me just write these things here. So you have L of U is equal to A U T T plus B U T X plus C U X X plus D U T plus E U X plus F U is equal to G. And then we have a discriminant. Delta is equal to b squared minus 4ac. Okay. Right. Okay, so with that in mind, this is going to hopefully remind you of the discriminant of a quadratic equation. This should remind you. Okay, so if I think of Q as being a dependent on x and y, is ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. All right, so and then the idea is that depending on these properties, it's like depending on the properties A, B, and C, it's like they lead to different types of conic sections, right? So depending on the discriminant, this leads to different types of conic sections. Okay, so as an example, you get hyperbolic, hyperbola, when your delta is greater than 0. You get a parabola when delta is actually equal to 0, and you get an ellipse when delta is less than 0. Okay, so this terminology sort of is what, if you will, motivates. It's like the referring to these type of equations as hyperbolic, parabolic, and elliptic, right? As you might expect, that corresponds to the value of this discriminant here. Okay. Okay, so the definition then, right, at a point Tx, right, the linear second order PDE is called the following, right? So the first one is hyperbolic if delta at Tx is greater than 0, parabolic if delta at Tx is equal to 0, but this operator is actually second order, so but a squared plus b squared plus c squared is not equal to 0. Okay. Then the third case is elliptic if delta Tx is less than 0, and then it's singular if a equals to b equals to c equals to 0. Okay. All right. So now we're able to do something about these equations. All right. So let's look at let's look at a simple case, right? So you have utt minus uxx equals to 0, all right, and then ut minus uxx equals to 0. So I'm going to just fix the coefficients basically, Then you have uxx plus uyy equals 0. All right, so let's look at what these correspond to. So, right, so the utt term is a, so this is a is equal to 1, and then here uxx is c, c equals to -1, right? So delta, which is b squared, so b is 0, so 0 squared minus 4 times 1 times -1 is equal to 4. 4 is greater than 0, so this is hyperbolic, right, which is what we had before. Okay, so ut, right, ut is d, so this is d is equal to 1, and then uxx is c, right, corresponds to, so c is equal to -1. Then delta is equal to b squared, b is 0, minus 4 times a is 0, times c, which is -1. So this is 0, right? So this is parabolic, right? Okay, and then you have uxx and uyy. Uxx corresponds to a and c, right? So a is equal to c is equal to 1, right? So b squared, so delta is 0 minus 4 times 1 times 1, which is -4, which is negative. Okay, so that's elliptic, right? All right, so again, this is just sort of a quick way of classifying partial differential equations, second order. You know, it's like second order, it's like linear, it's like partial differential equations. And again, the reason it's like to be aware, it's like of this classification is because what you'll find, it's like when one develops, so this is elliptic, sorry. What one should be aware of, it's like when you find, when you look at numerical methods for partial differential equations, is that they tend to be classified, it's like according to the type of partial differential equation it's applicable to. So you have numerical methods for hyperbolic systems, you have numerical methods for parabolic systems, and you have numerical methods for elliptic systems. Okay, so so with that in mind, it's like we'll start talking about numerical methods for, you know, it's like some of these types of PDEs. Right, so let me stop here.